In this talk, we are going to cover like what are the basics of quantization. Like we're going to start from the, from the very ground up, and finally conclude with how you can be using Pytorch native libraries or vanilla Pytorch for quantizing your models. I think one important point that I'd like to bring up is one advantage of using the native Pytorch API is it allows more migratability, like from stack to stack. So if your application isn't ready to be locked in, for lack of a better word, to a particular stack, it might be easier to just implement your application using PyTorch native libraries, native APIs, and that'll make it easier to take any of the outputs and plug them in any of the PyTorch ecosystem libraries. But I think Optimum is more than just PyTorch, so that it probably also supports TensorFlow models. Thank you, Chris, for that question. You have given me some reading to do today. So, all right, welcome, folks. We're going to start the presentation now and the workshop now. So today's workshop is going to be about having more efficient AI inference using PyTorch quantization libraries. One moment while I figure out technical. So today's agenda looks something like this. We are going to start from the very ground up. That is, you don't need any prerequisite knowledge about quantization, how any of the math behind it, because we're going to cover that. You also don't need any other prerequisite information apart from a basic understanding of how deep neural networks work. If you look at the agenda, you'll see some points marked with a C. Those are our coding exercises. One of them, the first one, is very hands-on. That is, the code is actually not there in the notebook already, and you have the option to fill it in as you follow along. But if you don't want to do that, that's fine. I'll be doing it anyway, so you can just watch the screen. It might be helpful if you wish to follow along. You might want to clone this repository. Let me just put that in the chat. I'm not sure if I can pin this message, but this is the repo that has all of the notebooks. Feel free to clone that, and you can follow along as we go down this workshop. I know being virtual, it's a little more difficult to be hands-on and be all coordinated. So totally okay if you just want to watch the stream. We don't need a GPU instance. That's one really cool thing. We are going to be doing quantization entirely on CPUs. If you have an M1 CPU, that might be a little difficult, but for all other x86 CPUs and even ARMs, you should be okay. Just give me one moment while I just correct my screen share. All right. So efficient AI. That's really the need of the hour because, I mean, we all know the environment is at risk and deep learning takes a lot of power. We'll just take a look at exactly why in the next few slides. So the simple truth is that the bigger your model, the better the accuracy. Like you just have to look at GPT-2 or Clip or even DALI to see what amazing results come, but at the cost of a lot more parameters. So the bigger the model, the more compute it requires, the more memory it requires to store all those parameters. And of course, that means a lot more power that it consumes. On the other spectrum, end of the spectrum, we have edge devices, that is models that are really small that can fit on microcontrollers at the edge or mobile devices. So a lot of mobile platforms have already widely adopted smaller models like MobileNet. These small models, they trade off accuracy to be a little more efficient in terms of compute. But a lot of inference still happens on data centers or not on the edge. And these applications which use data center inference, they tend to prefer more accurate but compute intensive models. Especially in applications which are critical, accuracy drops which are even below 1% are not acceptable. And because of that, we see that the power consumption by data centers is just doubling every year. So in this graph that you see on the screen, this is the power consumption at data centers running Meta inferences. So Meta being the Facebook app and WhatsApp and all of these applications. Together, you can just see that it has increased close to 3.5x in just about in less than 3 years. So we expect that as machine learning and deep learning technologies start to proliferate and more industries start to adopt these technologies, there's just going to be more power consumption and there's just going to be more inferences. And this is going to contribute very significantly to the carbon footprint problem that we're all facing. So what are some solutions for this? The first one is hardware and software co-design. This is, of course, the best in terms of the results. What this simply means is that when you're building software like deep learning applications or deep learning models, you build hardware that is super optimized for those compute steps. Like one really good example is TPU. The tensor processing unit is engineered to be optimal for matmults or for matrix multiplications. That is the cornerstone of any deep neural network. Also, along with that hardware, you also have very optimized kernels to run these operations specifically for that hardware. Like for example, you can run Pytorch models on TPUs using XLA, like Pytorch XLA. I'll just add that in the chat for your reference. The other solution is quite obviously just build more efficient models. So you just build architectures that need less parameters, that do more with less. So one really good example is the MobileNet. But one very obvious caveat over here is that this takes a lot of research. It's easier said than done. It's a pretty difficult topic, very non-trivial in nature, to actually build more efficient architectures. And also the other caveat is that even though they're smaller, the accuracy does drop. And so these models are not always good candidates for applications that are very critical in their requirements of accuracy. The final solution, like what Optimum offers, is model compression. So compression can be a lot of different things. There's sparsity, like just having more sparse networks and using not being like fully dense. There's also pruning, where you drop certain weights and you basically take advantage of the redundancy that is inherent in deep networks. And the other way of compressing models is quantization. All of these are very simple in the sense that they don't need any new architectures, software, or they don't need any new hardware. You can take what's existing, the model that already is there, and work with that to make it more efficient. So that makes it a really good candidate because you don't have to invest too much in new architectures and hardware design, and that makes it more accessible for companies to use and to reduce their costs of running deep learning models, and also their carbon footprint on the environment. So now that we are onto quantization, let's try to understand what it is. So as a concept, quantization's roots are in digital signal processing. So if you have like an analog signal, when you're converting it to digital, you're basically quantizing it. Like if you look at this GIF over here, GIF, you see it starts out with a high-res image, and then it slowly goes to low-res. But you can still make out like what it is. In case you didn't know, that was the Pytorch logo. And so the same techniques that are used in signal processing can be used to reduce the size of deep networks as well. So typically, deep networks, their parameters are floating point numbers. Floating point numbers are 32-bit. That is, they need 32 bits of memory to be represented. And with quantization, what we're doing is representing them in integers, which require only 8 bits. Because they're smaller, int8 arithmetic is lighter and faster on many CPUs that are that have specific features for int8 adds and mults, addition and multiplications. So when you go from 32-bit to 8 bits, there is an automatic 4x reduction in memory requirements. And because CPUs are optimized for this, you can see about a 2 to 4x reduction in how much compute or how many flops are required to perform the same operation on two numbers. So when you're, how do you actually go from 32-bit floating space to integer? That's what you have the mapping function for. So when you think about it, even the humble round function is a quantization mapping function, because it takes in a floating point number, like, you can see pi, and converts it to integer space, that is just a 3. And that's exactly what a quantization mapping function does. But you can imagine that just simply rounding that might not give us very good results. So what we use is a affine mapping function. If you look at the formula, at the equation, that looks very similar to a linear transformation, and that's exactly what it is. So you take a value in 32-bit space and you project that to int space. And you can see that there are two parameters that enable this transform, S and Z. S stands for the scaling factor and Z stands for the 0 point. We'll cover that in the next slides. By the way, if you have any questions, feel free to keep posting them in the chat. I'll be getting to them as and when we pause for breaks and just when I get a chance. All right, so coming back to quantization parameters, S is a scaling factor. So very simply, it's the ratio of the input range to the output range. That is when you're going from 32-bit to 8-bit, and your values have a minimum and maximum over here, and you want to sort of translate that to a min-max value over here. So alpha and beta, they represent the min-max of the input range, and alpha Q and beta Q, they represent the min-max of the output. So if your weights, if your parameters on the model are distributed between minus 0.5 to 0.5, then alpha is minus 0.5 to 0.5. And the output range depends on how aggressively you are quantizing it. So if your output space is 8-bit, that is you're converting to 8-bit integers, you're going to have a much larger range of values. If your output space instead is 2 bits, then it's going to be much smaller. It's in fact going to be just 4 integers. So your input values have only 4 candidates to fall into, or 4 buckets to fall into. We'll take a much closer look at this when we go through the coding exercise. The 0 point is the other quantization parameter. And you can think of this something as the bias term in a linear regression. So what it very simply, the only function it has is to adjust this translation so that 0 in input space maps perfectly to 0 in output space. So it's almost like um, you're syncing the origins in your input and output space. So that's what the 0 point does. But intuitively, you can think of it as the bias. Okay, it's time to code. So if you have cloned the repository, please open Quant 101. That is the notebook that we are going to be using um, for this exercise. Give me a moment while I share my IDE. Thanks, Nabila, for that question. I'm using 1.10, but there is no restriction on that. You can use whatever Pytorch version you are using. And if you run into issues, just let me know. I'll also put it in the text or in the chat, just for posterity. Can someone let me know if this is clear, like super visible, or do I need to zoom in any more? Cool. Thanks, Nabila. Thanks, Akshay. Okay. So first thing is, let's just get done with some prerequisites. Let's import all the libraries that we need. So I'm running this on a CPU AWS instance. I forget which instance is it. But when we take a break, I can add that to the text if you want to perfectly reproduce this or replicate this. So just importing all the libraries that we need. And let's also get out of the way some prerequisite functions. So this function just loads an image from either a file or a URL. This one pre-processes it based on the ImageNet mean and deviations. So you want to normalize it based on uh, the the mean and STD that it was used to train on. And we are using a ResNet, which was trained on ImageNet. So we want to use the same values over here. And yeah, these are just helper functions. They don't have anything to do with quantization. So we are going to use a ResNet 18 model for this demo. It's a really small model, should be fairly easy and fast to download if you don't have it already. So Torch offers, the Torch Vision offers these pre-trained models, and all we have to do is call pre-trained equal to true, and we get the ImageNet weights. Now, because we are doing inference on this, we want to go into eval mode, and eval mode is important because it modifies bash norm modules, which are more relevant for training than inference. We also don't expect to change any gradients, so requires grad is false over here. I just run a quick test that the model is working well. This is an image of a wolf. Okay, looks good. So we want to, what's really important to us is making the model faster and smaller. It's leaner and yeah. So we just write one helper function for that. And I've defined these. So this is the first part of the exercise. How do you actually write a function to print the size of the model? One quick hint is you can use os.path.getSize. And generally what you want to do is you take the model, you save it to a temp file on disk, you run os.path.getSize, and then you return that value. It's really simple, nothing too fancy. I'm not going to spend time writing it, so I have this here, but feel free to implement this yourself. And if you have trouble doing that, then you can simply run this to get the solution. So I'm going to paste this in. This is what it exactly does. You're saving the state dictionary, that is all of the parameters of the model, into a temp file. You find the size of that file and you print it. We also want to make sure that our model runs faster in inference. So we want to measure that. How we can do this is just very simply use time, like wrap your inference code with time.time blocks and just return the difference. And one important thing to do is use inference mode. That gives you a slight speed up by disabling certain things that are absolutely not used in during inference. Is anyone actually following? Like, is anyone actually writing the code? Like, do you actually want to write the code for this? Would you like me to wait while you take a stab at it, or should I just move on? Oh, that probably is because you don't have wget. Torch is not really inference mode. Chris, can you let me know what version of Pytorch are you using? And Gaurav, that's probably because you don't have wget, the utility installed. That's a Unix or Linux utility. What it does is essentially download this file and print it. So if you are not able to run wget, maybe you can just click this link and that should give you exactly the same output. Oh, yeah, Chris, that's because inference mode is a more recent feature. You might want to try updating PyTorch, but if you don't want to do that right now, that's okay. Just remove inference mode, or actually you can replace it with no grad. So I'm going to type it in the chat for posterity. There's no grad, right? Okay. So like I was saying, you simply wrap your inference code in time.time. Akshay, inference mode, it disables certain autograd features, which eval also disables certain autograd features, but inference mode is a little more aggressive. And for more detail on that, I can share a tweet thread that we posted on the Pytorch Twitter account, which kind of explains this in a little more detail. Maybe let's go into a break and then I can share that with you on the chat. Thanks for bringing it up though. So we have the module latency code in place. So now all we want to do is profile the ResNet model. And the simple steps for that is you load an image, you pre-process that image, that is you prepare it for inference for the ResNet, and then you run the inference while profiling it. So like I mentioned, the pre-processing is very specific to ImageNet trained models. And since we have a ResNet which is trained on ImageNet, that works pretty well. Fairly simple. So we see that the ResNet 18 model occupies around 47 megabytes in memory. And the latency for for an inference on a single image is around 40 ms. All right, so now we have a model. It's a pre-trained model. It's in FP32 mode, and if you want to check that out, all you have to do is think this should work. Yep. So we can see that the model's parameters are in 32-bit floating point, and the model itself consists of a lot of layers. Let's just see all of them. Like there's a whole bunch of conv blocks over here, and blah blah blah, and finally it ends in a classifier, um, which is a linear layer. So what we're going to do in this exercise is we are only focusing on quantizing the last layer of the model. Um, and for that, what we're going to do is we're going to separate the rest of the model from the classifier, and we're going to work on this, on the classifier only. So we make a copy of the classifier into FP32FC, and it's named that way because it is still in floating point. And we are deleting the classifier from the ResNet by replacing it with an identity module. And this literally does nothing. It's almost like multiplying by one. So it's a no op. It doesn't do anything. So right now, as of this cell, we have our ResNet model without a classifier, and we have the ResNet classifier in FP32FC. And just to make sure that everything is still working, sequential basically wraps two modules in a sequential order. And this should give us the same value as before, which it does. We extracted the last layer because we are going to focus on quantizing that, and we are keeping the feature generator separate. So you can think of the ResNet as the feature generator and a classifier. The feature generator is basically taking in an image and just going through it convolutionally to represent that in a vector in a tensor of 512 features, and that it sends those features to the classifier, which is the last layer. What we are doing in this exercise is we are manually going to try to fake quantize the last layer. So that's why we have removed it from the rest of the model. I hope that answered you, Gaurav. So we're going to first try to use rounding as the mapping function to quantize the final layer, the classifier. You remember that we went through this, and even the round is a quantization mapping function. So let's see how that works. What we're doing over here is we're replacing the final classifier's weight and bias with its rounded values. And that really does sound too good to be true. Like something that is, there's no free lunch, right? So just simply rounding the numbers, I don't think that's going to work, but let's see. Right. It takes in the image of a wolf and says it's a mosquito net. So clearly that didn't work. But it's good to understand a little more about why that doesn't work. So remember that we rounded the classifier's weights. Let's see what the weights were before the rounding. This shouldn't take this long. Sorry about that. This should not be taking this long, so I just interrupted it. But what it does is, I wish I had the image to actually show you. Try again. Okay, yeah, that's not working. I'm sorry. But what this basically, well, what this does is it plots the weights, and we'd be able to see that. Oh, thank you, Nabila. Yeah, it does give you a bit of an RHS tail, right? Can you let me know? Can you drop it in the chat? Like, what are the min and max values of the distribution just from the image? Thank you so much. So Nabila has shared what the min and max values of our weights are, and you can see that they're falling between minus zero point 0.2 to 0.7. So you can imagine what a round would do to this. It would just destroy all our weights and bring them to zero. Yeah, we just zeroed out our layer when we did this. So clearly, we need a more intelligent way to map to quantize our values. So what we're going to do is we're going to first rescale the parameters. So we're going to move them from minus zero point 0.2 to 0.7 to to a more appropriate range for rounding. Eventually, we do have to round it, but since we can't do it for values which are less than 1, we want to move them out of that range to much larger values and then round those. So if you remember from the slides, I'd mentioned that the output range depends on how aggressively we are quantizing. So the range of an 8-bit number, because it has 8 bits, the lowest value that it can be represented with those is minus 2 to the power 7. And the biggest value would be 2 to the power 7 minus 1. So given that we know that, we can easily write this function. But for the sake of time, I'm just going to put this in here. It's literally doing what I just said. Let's see how it differs. So clearly for 16-bit quantization, there's a lot more values that your floating point number can take when it becomes an integer. And that keeps reducing as you keep going down the bit width. So 8 bits can only take around 255 values over here. 3-bit quantization, which probably doesn't exist, takes about 7. And 2-bit quantization, which I know exists, it's surprising. It can take around 4 values. So just to summarize, like this is the output range of our quantized value. So we are going to use 8-bit quantization because that seems more uh, that's more useful. That's a more useful quantization bit width when we are trying to quantize our FP32 models without damaging accuracy too much. So the output range is going to be minus 128 to 127. And like I mentioned, instead of a simple round, what we're going to do is first transform it from 32-bit to 8-bit space and then do the round. And this transformation is going to look like this: y is equal to ax plus b. Must be a very familiar equation to you. And we already discussed what the scaling factor in 0 point does. So the actual quantization mapping function looks like this. You transform it, affine transform your value, and then you round it. So you define 3 functions for that. First of all, you need the parameters. You need S and Z, which depends on the input range and output range. If you remember from the slides, we had some formulae. I don't expect you to remember that if you don't already know it. So that's fine. Um, Once we have the parameters, we can actually run this function. So quantize would do that. It would plug in x, s, and z in this and return to you the quantized value of x. And dequantize is the inverse transform of that. So given xq, you want to get x back. And finally, wrapping that all together, given an x, given a value, FP32 value, you will first calculate the input range. You'll calculate the output range, which is based on our 8-bit quantization. Then you get the quantization parameters, which depends on the input and output ranges. Then you do the quantization function, and yeah, voila. So I'm going to do the same. Fairly simple and pretty straightforward so far. Um, you have the input range, that is just your min and your max, and you plug it into your quantization params function, and you just run it through the formulae, and you get your parameters. Very straightforward. Quantize, again, it's very straightforward. It's literally the same thing that we're doing again. And dequantize, if you notice, it's the inverse function. So we have our helper functions for doing the mapping. Given a FP32 value, we can directly now get the quantized 8-bit value along with the scaling and scaling factor and 0 point parameter that was used to facilitate this quantization. So now we can actually go ahead and try to quantize our classifier. Remember, it's the last layer. And right now, ResNet is just our feature generator. So in quantize inputs, what we're doing is we take in an image, we get the features out from the feature generator. Then we take those features and we quantize that, because these are going to be passing into our quantized classifier. And when it goes to this quantized classifier, it will go through the quantized weights and the quantized bias of the classifier and give us the final output. So we want to quantize the inputs to the classifier, and then we want to quantize the classifier itself. So remember I mentioned that int 8 arithmetic is faster, and that's because these operators run in specialized kernels, kernels which are specialized for int 8 arithmetic. So Pytorch has two options. You have FBGEM and QNN pack. FBGEM is for x86 CPUs, and QNN pack is for mobile and ARM CPUs. So we don't actually we are not actually going to be using those kernels over here. We're just going to simulate what quantized what a quantized linear operation looks like. And how we're going to be doing that is we have the quantized values. Everything is quantized right now. We have the input in 8 bits. We have the classifier in 8 bits. We're going to dequantize that. That is, bring them back to 32 bits, do the operation, and then return that value. And that's exactly what this function is doing. It takes in the quantized input, weights, and bias, dequantizes all of them, and does your add mul. So now we have everything in place, and we're ready to run this. So while we are in FP32, we take the image, pre-process it, pass it to the feature generator, and get the features out in FP32. And now we move them to int 8. So we quantize our features, quantize our classifier. Oops. How did that happen? Four-dimensional input for 4-dim weight. That's because our ResNet it has these weights. We've got 2-dimensional input of size 151, 2. That's strange. Do you mind if I debug while we are doing this? Just make sure. Oh. So it looks like the identity function didn't run. Sorry about that. Let me just make sure. That's fairly odd. My apologies. Um, I did not encounter this when I was testing. Um, yeah, you're right. Thanks, Gaurav. What had I done before then? In the interest of time, I'm just going to go ahead with this code and talk through it. I hope that's okay. My apologies again. And I'll correct the notebook and upload that to the repository as well if you'd be interested to run this later. That's not very ideal, but okay. So I'm going to try to talk through what this does. So we quantize our inputs and we quantize the classifier, and then we take we when we are passing it through, we dequantize them both, and then do the mat mul and return the output value. So what we actually get is that the outputs of the quantized model, the fake quantized model that we just developed right now, and the outputs of the non-quantized, the original ResNet, they're pretty different. And that's given by the quantization error. Like when you take the delta between what is the quantized output and the non-quantized output, um, that tries to give you how much change has the quantized model actually implemented, and it is actually pretty huge. Like at 0.001, that's fairly large for values that typically take those are typically around that. But spoiler alert, actually, it's the same prediction. Um, the quantized model and the non-quantized model still predict wolf for that same image, and that would have worked with these as well. I wonder if this one works. I'm just going to try. I'm really not sure what changed. I think something probably changed when I was updating the code to be a little more readable. But I don't want to waste your time by trying to debug this. I hope this gave you a pretty good sense of what is happening over here. Yes, I can come to that in just a moment, Rajshri, about use cases where quantization is used. Most typically, it's used where models are running on mobile. So you have very limited space available for your model. So quantization reduces, it drops in the size. That's a very typical use case. And the other use cases are just for any prediction where the quantized model still gives you the same performance and same accuracy performance, while just being more faster and consuming less memory and compute. So because I ran this quite a few times, I remember the numbers, Gaurav. The accuracy actually increased slightly when we did this quantization. And we'll probably see this more in the next coding exercise as well. It's kind of surprising, but the accuracy did actually increase by a few, by a few bips, by a few decimal points. The speed itself did not change very much because we aren't actually using any quantized kernels in this exercise. But we will take a look at how performance compares between non-quantized and quantized paths models. Yeah, Akshay, thank you. That is slightly confusing. The dequantization part in this exercise comes in because we are not actually using the quantized kernels, so we can't actually run the add mul operations on the quantized tensors. So what we are doing is dequantizing it, doing it in FP32, and returning that value. So the advantage of this is that your weights and your tensors are still in int 8, but realistically, this is not how quantization is done. This is just to give you an idea of how what the flow is. This sort of fake quantization is actually used in quantization aware training, which we will be covering in more detail in the slides ahead. Okay, let's get back to the slides. Sorry, the code. So we have a fairly decent sense of how quantization works, and now let's take a look at some of the building blocks that are used in Pytorch to actually run this quantization. So given a FP32 tensor, what are the what's the process of actually converting that floating point tensor into int 8? Great question, Norman. I will be covering that in the next section of this workshop. That is actually the most important part, I think. So, so if you look at this figure, this is quite simply how the journey of a tensor in floating point 32 space to int 8. So so you pass the tensor into this quantize module, which also takes in the quantization parameters and the final output data type. So int 8 in our case, and then outputs the quantized tensor. What's important over here in this figure is how the scale and 0 point Q params are calculated. And that's, the methods that are used to calculate this are called the quantization schemes. This is fairly detailed, so I'm going to skim really fast through this. But if you do have any specific questions, feel free to stop me and let me know. So there's two sets of schemes. Both are differing in how they modify or how they determine the Q params. We'll take a look at both. So this one is fairly straightforward again. You usually for images, you have tensors which have multiple channels, right? You have like if it's an RGB image, it has three channels, one for R, red, green, and blue. And as it goes through the convolutional layers, the number of channels increase. So in per tensor quantization, you simply have one set of Q params for all of the channels, just one S and Z. But per channel quantization, as the name suggests, you have a separate S and Z for each channel in the tensor. So it looks something like this. Uh, let's say this is your input tensor. Your input tensor, it has three channels, and you can see that over here. You can also see that over here. And let's see what per tensor looks like. So remember, per tensor is just one scale and 0 point for all of the channels. So we define that over here, just example values. We have one scale and one 0 point. And to actually do the quantization, there is a helper function in Torch, quantize per tensor. You pass in the input, you pass in the scale and 0 point, and the D type, exactly like what we have over here. The input, the scale and 0 point, and the output D type. So you can see that our input was, you can compare our input and the output. 5827 has become 5800. 6351 has become 6400. And you can see what were the scale and 0 point Q params used for this quantization. All of these things are wrapped in the quantized tensor. So this makes it really easy to dequantize this value. In fact, these are actually the dequantized values that you're seeing, because they are the actual quantized values are in integers. Similarly, for per channel, you define what's your channel axis. That is the first dimension in your input tensor is going to be is most typically your channel. Sometimes it's a batch, but here it's the channel. So you have three channels. You have three channels, so therefore you'll have three sets of scales and three 0 points. And when you do the quantize per channel, very similar results, but it does differ in some places. That's because you're using different scales for these two channels. Yes, Gaurav, great question, and thank you, Nabila, for answering that. Under the hood, Pytorch has already quantized that to integer, but when you call that particular tensor, it returns to you the dequantized values. So that's per channel and per tensor. We also have symmetric and affine quantization schemes. Now, before I open the figure, so symmetric, essentially, what we are doing here is we are calculating the input range, right? So given a bunch of tensors, you want to see what is the minimum of that tensor, or what is the minimum and what is the maximum, and then you want to use those as your alpha and beta. So symmetric and affine define how we are actually calculating the alpha and beta. So the symmetric scheme calculates the alpha and beta symmetrically around 0. They're good for quantizing weights, but not so much for activations. And the reason for that will be clear in this plot. Let's take a look at the activation, the distribution of the activations. So typically your activations follow a Pareto distribution like you see over here. You can see that a lot of the values are around 1. They're between 1 to 1.5. And there's literally no values left of 1 or less than 1. But because we use a symmetric scheme, we have taken the max value over here 3, and we have taken the clipping range as -3. So these are symmetric around 0. This is pretty wasteful because all of the space in the output range is going to be unused. Your activation is never going to be less than 1, and perhaps never less than 0 as well, um, depending on the activation function you use. So all of the space that has been reserved in the output range is going to go to waste. That is, effectively, you're using much less buckets to represent your activation values. So you definitely don't want to use symmetric quantization for activations, but they actually work fairly well for weights because you can see how the weights are normally distributed, and it makes more sense to have a symmetric clipping range. For activation, what's better is using an affine scheme. And what affine does, it just takes the direct minimum and the direct maximum and uses that as the clipping range. So there's no wastage at all. It's pretty tight. It uses the entire output range to represent the input range. So when you we have totally 4 different schemes. You have affine and symmetric, and you have per channel and per tensor. So a permutation of all of that gives you affine per channel or affine per tensor, and this way you have 4 different quantization schemes. And all of that is wrapped in what we call an observer. An observer is also a module in Pytorch. They have a forward function. It just wraps all of this so that you don't have to do it by yourself. So I'm not going to go into too much detail, but you have various observers available in the Torch namespace. And I have like a sample input over here. And all this does is it compares how the scale and 0 point differs for different observers. So all of them use different algorithms under the hood. Histogram observer actually buckets your input into like literally buckets your inputs and uses that. Nabila, I'm not quite sure. Operator sounds like a function or a mathematical operation. So or basically a tensor manipulation. That's how it is used in Pytorch. I'm not sure if Onyx also uses the same terminology. All right, so we have actually gotten past the tough things over here. We have looked at the quantization schemes. We have looked at the observer, which uses these quantization schemes, and now we'll see how we can wrap all of that together into one object. And that one object is a quconfig. Literally, it's quantization configuration, and this gives us the knobs to turn when we are quantizing a model. So in a quconfig, you can specify what observer you want to use for the activation and weight separately. You can specify what quantization scheme you want and what is the output data type that you want to use. So this offers a lot more control in how you're quantizing your model. If you know, for example, that your model is a special snowflake and it does need a symmetric quantization for your activations, you can totally do that over here by creating your custom quconfig object and plugging in whatever observer and Q scheme you want. But to make life easier, Pytorch offers some default quconfigs out of the box. So you have your default per channel config, and if you take a look at this, the activation is defined over here, and your weight observer is defined over here. And similarly, you have all of these. We've covered a lot so far. I mean, if you have stuck with us, congratulations. It's a lot to take in. Feel free to take a break. Let's take a break for 5 minutes. And when we come back, we're going to dive into the good stuff, the meaty stuff, where we're going to talk about what are the quantization techniques available in PyTorch. We're going to cover static quantization, dynamic quantization, and even QAT, which is um, which is more fun. Let's just leave it at that. So let's take 5 minutes and come back. Meanwhile, please post your questions in the chat. I'm happy to answer them right now. That's exactly right, Akshay. You have the right idea. Because per channel has more quantization parameters, you can imagine that there are going to be more operations, and per tensor has just one. So, I'm sorry, the per channel has more parameters, so you're going to store more parameters depending on how many channels your input tensor has. So, it is a compute trade-off, but it's it definitely improves accuracy when you use per channel, especially on images or especially on outputs of convolutions. That's a really good question. And in fact, when we talk more about the techniques, we are going to cover this. We are actually going to go through an entire workflow that you should be using when you're evaluating how do you decide whether to use this technique or that technique, how do you decide whether to use which quantization scheme. Yeah, there is a lot of choice, and that's not always a great thing because then it puts us into a dilemma. But we do need all of these various options for different use cases. So the way to actually tackle that is to have a very informed, take a very informed approach to which um, technique to use, and I'll be talking about that in the next section of our workshop. Gaurav, the observer, it accepts any of the input tensors. So you have your floating point tensor. It goes through the observer, and the observer, as the name suggests, observes. So it calculates the minimum of the input. It calculates the maximum of the input, and based on the specific observer that you use, it calculates the input range. So the alpha beta that we previously discussed, it observer calculates that. Yes, Nabila. These methods are applied before any serialization. Um, I'm not quite sure how optimum works under the hood, but here we want to typically use our PyTorch models natively to quantize them. So we'll continue in the next minute. So you have a few different ways to do quantization. The first major set of techniques is post-training. That is, you have a model that is already trained. You are very happy with its performance in floating point, and now you want to make that into integer. So for that, you have a couple of different options. The first one being dynamic quantization. So what dynamic does is it quantizes only the weights. Now, remember, stepping back a bit, the model has majorly weights and activations as floating point. Both of them are candidates for quantization. Dynamic only quantizes the weights. Let's take a deeper look into that. So the weights are quantized, but any of the activations that are coming into the layer, they're quantized on the fly. That's why it's called dynamic. Dynamic quantization is best used for models like for layers like LSTMs or transformers. That's because these layers have very their weights are very large. They're going to occupy a lot in they're going to occupy a lot of memory. So pre-quantizing them generally improves performance in terms of memory and compute. And dynamic quantization will work best with smaller batch sizes. That's because with smaller batch sizes, you have smaller activation sizes. And because you have smaller activations, you have less overhead in quantizing them on the fly. So when you're using dynamic quantization, just remember these two thumb rules. It's good for LSTMs and transformers and even linear layers, which have very heavy weights. And it works best with smaller batch sizes. And this is the simplest approach to use. It's literally one line in the API. So if you see the code over here, you've loaded your model, which is an FP32. All you have to do is call this quantize dynamic, and that's it. Like you can use the model as it is, or you can script it and then deploy it for even faster inference in C++. And along with dynamic, you have static. So this does the weights as well as the activations. So weights are pre-quantized, just like dynamic quantization, but the activations are also pre-quantized. And this is done on expected inputs. So you're doing this before you're actually deploying your model, right? And how do you know, like, how do you quantize your activations? So you use representative data to get a sense of what are the min and max values typically encountered, and then you use those to have your quantized activations in place. So because not only the weights but also activations are quantized, this inference is much faster than dynamic, but more steps are involved. In fact, quite a few more steps are involved, and we'll just see that right now. This should give you a sense of how static quantization works under the hood and just demystify the whole thing. So let's say you have a very simple model which has two layers, a linear layer and a ReLU activation. The first thing you need to do is try to modify the model. You want to insert the quant stub and the dequant stub. And what these objects do is it's like a gateway into quantized space. So in your forward function, you're getting an input in FP32. When it passes through the quant stub, it knows that now it's in quantized space. Uh, and dequant basically lets it know that we are back into FP32. So once you have done that, the next step is module fusion. So module fusion, basically you take models that happen one after the other, that are called one after the other, and you fuse them into one single kernel. And what this does is it just increases performance. Instead of doing multiple like linear and ReLU, now it's just going through a single kernel over here. So this makes inference typically faster. And once we have that, we prepare the model. So this is where the observers come into play. Calling quantization.prepare on this model, it's going to insert observers based on where we have the quant and dequant stubs. And finally, we calibrate the model. And what this means is, like I mentioned, we feed the model with sample data, with data that it is expected to encounter in production. So the sample data should be very representative of the test workload. Like you can't just have random data for calibration, because that will totally skew the model's statistics. So you want it to have data that it is most likely to receive. And one good way to do that is using the validation set. And finally, we have everything in place. So we simply call .convert, and this takes in all of our FP32 operators and converts them to the quantized version. Deploying is very similar. We script it and then we save that. So we're done with post training. The other paradigm in quantization is quantization aware training. So here we aren't done with training just yet. We have a trained model in FP32, but we train it a little further so that it knows how to deal with quantization errors. So the model is actually optimized on the quantization error as well as the training loss. And quantization aware training provides the best accuracy amongst all of the techniques. But because you need to retrain the model, and sometimes that can go into a few hundred epochs, it's pretty expensive. Like it's compute intensive. It takes time. So this is generally preferred when when you really need the best possible accuracy, and it's not negotiable. So this is a simple comparison of a few models. You can see that the accuracy doesn't change very much when we are moving from FP to int8, especially for the image models, and BERT has no accuracy change at all. And you can see that the CPU speed up is pretty sizable. Like it's more or close to double, and for MobileNet, it's 4 times. And MobileNet was trained on Q80, so even though it's a very small model, the accuracy has not dropped or degraded by too much. Akshay, good question. You don't have to do any of that because Pytorch handles that for you. Um, we'll take a look at that in the coding exercise that's coming up. So I'll go through this very quickly. There are two ways to do this: eager mode and graph mode. The code that we just saw on the slides right now, we're all in eager mode, and that's a very manual process. What we want is a more automatic, which requires less code writing from our side. So we use graph mode for that. And we'll be using graph mode for FX graph mode for our coding exercise now. So this is the flow chart that you generally want to use when you're trying to decide what to use and how to use it, which features to use for your model. Again, we're going through this in the exercise. So if you're following along, please open the Quant Workflow notebook. So let's get some prerequisites out of the way. So in this exercise, we're using a ResNet model that has been fine-tuned on CFAR, on the CFAR dataset. So revisiting this flowchart, we're going to be going through this step by step. The first thing we want to see is if our model it has more than 10 million parameters. The reason for this is that the larger the model, the more inherent redundancy there is in the parameters. So that gives us more degrees of freedom to drop precision. But again, it's a thumb rule. It's not strictly applicable. So take it with a grain of salt. Like for example, you can see that MobileNet actually has only 5 million parameters. So technically, by this thumb rule, it's not a great model to be quantized, but as we saw in the previous slides, using QAT on a MobileNet gave us almost comparable accuracies, almost equal accuracies. The next thing we want to see is that we have a floating point checkpoint, a floating point model in the first place. So we do have that over here. I have a trained model, Resonate 18 on the CFAR. There's also a Resonate 50 model if you want to try that on your own. And we can see that it is in 32-bit. Now, before we proceed with quantization, we want to switch that to eval mode. And finally, we want to make sure that we are using a supported backend. So right now, x86 CPUs and ARM CPUs are supported. And we want to set the correct backend value. So I'm using an x86. So I've set the FBGEM backend. If your machine has an ARM chip, then it will you will be setting the QNN pack. So let's establish a baseline for FP32. So the FP32 model takes around 45 megabytes, and the accuracy is around 87.5%, and it's taken around 86 milliseconds on the test set. The next thing we want to do is see what is our model architecture. Like I mentioned, recurrent and transformer layers, dynamic quantization works best because we just want to reduce the bottleneck of our weights over there. For everything else, static quantization works pretty well, especially convolutions. So our ResNet model consists of these layers, and the ones eligible for dynamic quantization is only the linear one, so just one layer. And that includes 5,000 parameters. But the layers which are good for static, there are about 21 of them and close to 10 million parameters. So clearly static quantization is going to work much better in this case, but let's try dynamic just to see how it looks. So I have a few links here to the dynamic API and the tutorial if you'd like to learn more about how to use this. But all of the cells right now are going to follow a very similar format. So we're going to use the default qconfig that's offered in Torch. And we set that in the qconfig dictionary. This basically tells the quantization module that we want to use this configuration for all of the layers in the model. So we just prepare the model and then we convert it. All of the stuff, all of the other things are handled by Pytorch automatically under the hood. So we have our dynamic quantized model in this. You can see there's not much of a change from our floating point model. It's barely reduced by less than a megabyte. The accuracy is about the same. The time has reduced by about 100 milliseconds. This was around 0.86 and now it's 0.78. This is because there's not much of a change because we only quantize the linear layer in the entire model. So what we're going to do is now try static quantization. We covered this. Using eager mode is very manual. It does all of these steps. But using FX graph mode automates all of this, and we just have to call two functions. Prepare FX does this under the hood automatically, and convert does this. That makes requires a lot less code writing. So the qconfig dictionary offers a lot of control in how you want to how you want to approach quantizing your model. So by default, you're going to have the default qconfig for all of the layers. But then if you want to change that for each module, you can do that over here. So like for example, if my model had a add and I don't want to quantize that, I can simply have a none over here, and that just skips quantization for that particular operator. So we are not going to do any of that. We are going to keep it pretty simple and use the same configuration for all of the layers. And it's again just two function calls. You first prepare the model, then you calibrate it, and then you convert it. Let's see how this performs. Oh yeah, thanks, Jerry. It is going to be much more easier to parse through. So remember, the floating point model was around 48 megabytes. That has reduced to less than 12 megabytes over here, a 4x reduction. The accuracy, like I previously mentioned, has increased slightly. The time has also halved. So static quantization is pretty strong. Like the reduction in the memory that it takes is a direct 4x reduction from 32-bit to 8 bits. And you can see that even the time has dropped by half. But what's very interesting is that the accuracy has not changed. In fact, it's slightly improved. So I guess nature does just wants us to use lighter models. Anyway, so now that we have done static and it looks really good, but let's say we still need better accuracy. So what we want to do is a sensitivity analysis and selectively quantize the layers in our model. So in sensitivity analysis, what we are doing is trying to evaluate which models suffer the most when we are doing a quantization on them. And when we are doing selective quantization, we disable quantization for those sensitive layers. So the one way to do that is to use numeric suite. It offers a bunch of tools to do this comparison and calculation of how the quantized and non-quantized layers compare with each other. So the function that we use over here is compare weights, where we pass in the float parameters and the quantized parameters. And then we try to calculate um, the SNR, basically the signal to uh, uh, quantized noise ratio. It looks something like this under the hood. Like you have the same data which flows through the float model and the quantized model, and it compares the outputs at each layer and tries to see how much information has been lost after quantization has been after quantization. So we are comparing our floating point resonate as well as along with the statically quantized resonate, and we get a bunch of values for the SNR. We take a look at the most sensitive layers. Like these are the layers which have the least SNR. That is, the noise is much more than the signal. So what we want to do is disable quantization for these sensitive layers. So the way we do that, again, is use the qconfig dict. We get our sensitive layers in this variable, and we just append none to that so that quantization skips for these modules, for these layers. So you can see the size has slightly increased because we skipped quantization for a few layers, but the accuracy it's still better than the floating point value. The time is still less than floating point, but a little more than the fully quantized model, as you might expect. So we are progressively going, fine tuning our quantization process so that we can achieve a good trade-off between performance and accuracy. Finally, we go through quantization aware training. Like if none of this has worked well for us and we still want better accuracy, the final option that we can try is QAT. Now, remember, this is a much more involved technique because it requires fine tuning the model. But let's take a look at what that looks like. So I have my default QAT config that I'm applying to all of the layers. So QAT is slightly different. You first switch the model back to train mode from eval because we are going to be training it. We prepare it for QAT. What this does is it prepares the model with fake quantize modules, which is very similar to what we saw in the 101 notebook, which takes in the quantized values, dequantizes it, and tries to get the quantization error, and then appends that to the loss, and then optimizes on top of that. So you prepare the model for that, you train it, and then you convert it. Very similar to the previous techniques that we have seen. I'm not going to run this because the training takes quite a bit of time, but I have already trained this here. So I am just going to show you what that profile looked like. So the size has again dropped by 4x. The accuracy has reduced a bit over here, and that's because it hasn't trained enough, and also because we're using a small model. But you can see that the time is also much lesser than the statically quantized model. Yeah, this was a lot, but this is kind of how you approach a workflow very comprehensively. Just to go through it again, we first want to make sure that our model is eligible for quantization. That is, it's large enough. We have a 32-bit checkpoint, and we are actually running it on a backend on a hardware that is supported. Once we do that, once we establish baselines, we want to first try dynamic quantization because that's just simpler. If we are happy with that, then great, like we can stop our process here. But if we want better performance, that is, if we want the model to be faster or occupy less memory, we try static quantization on the entire model. This will reduce accuracy typically. So if we want to reduce how much accuracy degradation happens, we do selective quantization. That is, we identify which layers are most sensitive, and then we disable quantization for them over here. And if you're still not happy with the performance or accuracy, we try quantization aware training, the most effort intensive step. Um, I think someone had asked this question before. How do you set these per channel and the quantization schemes? And happily, the default queue configs already take care of this for us. So the activations in the default queue configs, the weights use the per channel and symmetric quantization, and the activation uses your per tensor affine schemes. So that brings us almost to the end of the presentation. Just to wrap up, I have a last few slides. So what's coming next in Pytorch quantization? We are really excited that graph mode is going to be moving into beta. It's going to be much more stable, and the API is going to be more like you can. the API is going to be more stable, and you can start using that and trying it out. We are also opening support for custom backends. So if you want to be running quantization on more than an x86 or an ARM chip, we have an RFC for that to understand how to contribute to to the library to implement support for these backends. We are also working on tighter integration with the Torch Vision, Torch Audio, and Torch Text libraries. For example, Torch Vision already has a bunch of quantizations, quantized models. And finally, defined by run quantization is the next paradigm that we are excited about. That makes the quantization process even more automatic and supports a much wider range of models. So these are some of the resources that you can use to learn more about how to quantize your models. I'll add all of these links to the chat so you can refer to them later. Thanks for hanging on. I know this was a lot to take in, but thank you for sticking on. And please drop in any questions that you might have. It does not always improve accuracy while speeding it up. Yeah, there is no free lunch, right? I think sometimes you get lucky. It's still a very empirical exercise. Like you want to run it on models and see how it works before making a decision. There is not much very robust theory to support or to determine which models will work best. Unless I'm wrong, Jerry, please correct me if I'm. Um, in this case, we got lucky, probably because it's a small model, and we are also using it on the CFAR data set, which is fairly simple. But as you go to more complicated data sets, um, it you might see a reduction in accuracy. So if there are no other questions, I think we can wrap up. I'll add the resources in the chat right now so that you can refer to them. Oh, great question, Zain. I I think one of the best resources is to it depends really on what you're looking to keep in track of. So if you want to be more aware or familiar with what new features are being released or being worked on in real time, I think the GitHub repository is the best place. Like if you just start it and put your notifications on, you can even follow topics and tags over there. So you will get a sense of what new code is being written, what new code is being published, or even what new features are being discussed. So that's like the best or the most cutting edge um, uh, stuff that you can stay up to date with. For more user oriented features, the Twitter account is a really good place to be. Uh, we post very often the important things in tweets. So, you don't have to read too much. You can get a quick understanding of what's new and what's latest and greatest in Pytorch. If you want more longer, more in-depth understanding of the new things, we have two blogs. Like there's one on the Pytorch website itself. Let me just type it down. pytorch.org/blog. And then there's the Medium, um, PyTorch Medium site, microsite. This one has stuff that is more oriented around use cases, and the official blog is more technical. The Twitter account. Personally, I follow the Twitter account because it's just more efficient. Like you get to understand more in less. Oh, so we discuss differences. Um, that would be a difficult question for me to answer because I am honestly not very familiar with Optimum. But let me take a look at it right now. I should be knowing about this. Oh, I think Optimum is really cool. I briefly watched Philip and Lewis's stream today morning. I would say that it offers many of the same advantages as PyTorch quantization. I'm not sure if they use PyTorch libraries under the hood, but it seems like they support the same techniques in quantization as PyTorch, but additionally with support for Onyx runtime and INC. So that's really cool. I think from what I've read in the forums, developers have had difficulties running quantized models like PyTorch models on ORT. So I think Optimum is pretty cool. And they offer more than just quantization. This pruning and what's under optimization. I'm not sure about that, but there's also pruning. So that's even you can more aggressively compress your model. So I think that's really good. Yeah, thank you so much for sticking on. Apologies again for the little issues that we had in the beginning. I will update. In fact, I think I'll update the resources on the GitHub repository so that you can see it over there on the README. And then also make sure that the first notebook runs fine. So I'll update the GitHub with that as well so that if you'd like to try it out, you can. All right. Thank you so much for staying and have a great conference ahead of us. I'm excited to see what everyone else is going to be talking about, and maybe I'll see you there in the chat room.